going to be talking simulation and computational fluid dynamics with a brilliant engineer. So we had two engineers this morning, pretty big name, Ross Brown, Pat Simon, and now it's Mr. Ray Leto. I had the privilege of meeting Ray again, maybe 10, 15 years ago.
Yeah.
And Ray has this incredible talent, I've said that before, to explain the most complicated things in such a simple way. We had TSAuto yesterday evening, Danny Nolan, who did also a brilliant job. So it is 9:59, and I think Ray is prepared to share with us some really cool things about CFD. So Brad Gilly, we're going to let you take over. And we're going to be on for something really cool for the next 25 minutes.
Thank you, Francis. Thank you very much, Judy. And I'm pretty excited about this because I truly enjoyed it the last time we got to do this, Ray. To be honest with you, for someone who really has pretty much zero understanding of what you do, it does sound pretty cool to say computational fluid dynamics. So the good thing is we have you actually on here to describe for us. The title of this is Mapping Aerodynamic Performance Data Using a Streamlined Computational Fluid Dynamics Workflow. So
that's
with that, it is a mouthful, but again, it'll make you sound really smart at parties, that's for sure. Even smarter when you can explain it like you can. But give us an overview of what we're talking about here today. And I know you come fully prepared for these, so I'll turn it over to you.
Yeah. So yeah, thanks, Brad. And yeah, of course, it's good to see Francisque and Judy again, and obviously watching Marshall and Zach for the last bit. It's been fun. So I'm a little distracted thinking like a race fan and enjoying that conversation. But I'm kind of, the idea today is kind of circle back on the chat that we had last year and the talk that we did about kind of what you can do or why you would even do CFD or aerodynamic study on a racing vehicle and what you can get out of that. So we're just going to kind of build on that this year and talk about, maybe dive down into how we've created a bit of a streamlined application or a method for getting repeatable results in CFD. So on the computer, just like you were going to the wind tunnel and doing repeated tests, or going to the racetrack and doing repeated tests. It's the same motorsports mindset of being disciplined about things and making a quick process to be able to study the car and do development. So that's what we're going to dive into today, and just show you a brief overview of how we go about doing that here at TotalSim.
This is fantastic, and it's really amazing the industries within which you guys work and everything that you do for the racing industry as well, and what you have to offer. So when it comes to exactly what you talked about, being able to do this inside the computer, getting repeatable results and all of that, but where do we start with this here?
Well, let's see. I don't know. Maybe the best thing to do is I'll share my screen. I got a bit of a slide deck to run through, and maybe a couple. I've kind of captured a couple of videos of us working through the application, and then I can show you some results and go from there. How's that, Brad?
Oh, perfect.
Okay. All right. There's my calendar. You guys don't need to see that. We'll go to the PowerPoint, and hopefully you can see my screen now.
Yeah, we can.
All right, great. So just we'll start with a little recap of kind of who we are as TotalSim and our racing background. TotalSim actually started as Advantage CFD fundamentally back at Reynard in '98, where Rob Lewis and Adrian Reynard decided to kind of create a separate entity within Reynard that was going to do CFD. And this was pretty forward thinking at the time. There weren't not even every F1 team had a CFD department at the time. And in fact, that the kind of the history of Reynard is where TotalSim evolved. Advantage CFD stayed with the F1 team, BAR, and then Honda F1. And in 2007, basically the outside consulting part of the business, which was always part of it, like doing outside work that didn't focus on the F1 team, was spun out to be TotalSim. Rob Lewis and a bunch of the guys that were at Honda Advantage CFD moved outside. At the same time, we've kind of started talking about doing that here. My business partner, Nathan Eagles, and I Nathan was at Advantage CFD back in the beginning at Reynard, worked on all the wind tunnels for them at the time and did some car work. He started the CFD department at Williams F1 in around 2000. So he was the first CFD engineer there, grew that up to a team of probably 30 or 40 guys before he left, and we started this together. So we're based in Columbus, Ohio, and Pasadena, California. We've got about 12 engineers. Most everybody's aerospace engineer. We do a lot of compute. We're kind of a DIY shop. We build our own computers, do a lot of our own software. We're fortunate to be in Central Ohio, where we get to have a fiber connection to a supercomputer center that we also use. Still do a lot of wind tunnel testing and other things related to race cars. But some of the other things we do, we've kind of diversified and taken that motorsports mentality of quick product development and applied it to different industries, which is pretty neat. I mean, a lot of the guys that are on this week, you know, are focusing on motorsports business, but they have other businesses, whether it's defense or they have other lines that they work in, because for some reason, you know, that motorsports work ethic or mentality, it really works well in other areas, that kind of hard-pressed time frame thought process. So we're in oil, you know, we've done oil and gas work, medical devices, a lot of aircraft. These days, aircraft are UAVs and urban air mobility. So we're doing a lot of that. Sports, our UK office does a lot of cycling and sliding sports work. So it's pretty interesting. Anything that has airflow, fluids, gas, water, oil, we love to work on it. So as I said, Brad, kind of going back and talking about what we did last year, we tried to show like what can Aerodata tell you? What can you do? So it helps, as we said, it helps you understand your car better. So I'm sure as you know, if you guys watched Danny yesterday, when you're doing simulation stuff and you're thinking about engineering a car, you have to consider all the things that go into it. It's the tires, the dampers, the springs, the kinematics, the suspension. And a big player these days is obviously aerodynamics. So we need to be able to capture that, understand it, and then possibly even model it in these lap simulation programs, or model it in another way to help us make decisions, both in design and on the race weekend for setup work. Mostly the biggest benefit we see is that, you know, understanding your car and then also being able to optimize what you have. It's not always a development task. A lot of times it's just optimizing what you're given. I mean, we know these days racing is a lot of, you know, spec series or light cars out there, you know, even at the top level, IndyCar, NASCAR, you know, the cars are essentially the same. And then it's about optimizing what you're given. So understanding these things are really important. So we want to understand the trade-offs between lift and drag, looking at, you know, optimizing that around laps and trying to figure out where we want to be. So we do that by creating a map of this, what we call mapping of the aerodynamics. And we showed this last year as well, where we're looking at plotting with this particular small formula car, like an F3 car, we're looking at different ride heights, so front and rear ride height changes, and has the, you know, shows how the forces, both the lift and the drag, would change with those ride heights. So we can say around the lap, now we can understand what's going on and possibly change that or optimize it, make sure that in a mid-quarter situation when we need the downforce, we're in the best attitude that we can be. We could do that through springs or whatever it is, but at least we have the data to understand what we're doing. So how do we go about doing that? What we've done here at TotalSim is we have a manual method, but we've also scripted that up so that our engineers and other people that use our tools have a repeatable way of doing it. It used to be in the beginning with CFD, it was kind of handcrafted. And some people still do it this way, where you start with some geometry, you have to build a mesh, you have to understand all the boundary conditions. You're basically building a virtual model of a wind tunnel every single time you do that. So we've automated a lot of that. And we have one example of this app is a TSAuto is what we have. And it's basically a complete workflow for repeatable process for doing vehicle aerodynamics. And it could be race cars, could be road cars, could be a bicycle. but something that runs on the ground, that we have that type of wind tunnel virtualized so that we can do that. Now, in order to do this, we have to, obviously we have to get this, this object, this physical object into the virtual world to do that. So typically the way to do that is if you're a designer or a manufacturer, you're going to have CAD or computer aided drawings, 3D drawings of your vehicle or your object that you want to study. And that's typically the way that it's done. So all this stuff is drawn in a CAD software. That 3D geometry is then uploaded into the CFD workflow. We do a lot of naming so that we can treat things differently, like the wheels are rotating and the body's stationary, the wings are set at their certain point. We can do the kinematics of suspension. All that geometry has to be taken care of. And I don't want to minimize the difficulty in doing this. It's a non-trivial exercise, and I think like many processes, that upfront work pays benefits in the end. So if you have that information, it really comes through. In the end. Now, there are instances where people don't have geometry, so we deal with that through reverse engineering, things like that, which we can talk about. But once the geometry is uploaded, and then we set up essentially what we want to test. So how fast do we want to go? Therefore, how fast the wheels are spinning, the road is moving, the air is blowing. What angle do we have the car at? What ground clearances do we have it set at? What wing angles? All those things are set up in there. And then we'll run and process that data through CFD simulation, which for most cars like this can be kind of accomplished in an overnight fashion, like 8 to 12 hours. And we're talking about running on a supercomputer on maybe a couple hundred cores simultaneously, and we'll get an answer back overnight. And then we want to post-process the data. We want to get all that tabular information, the forces, summary. We want to look at some images. That's the best thing about CFD, is we can actually see what's going on with the airflow, maybe try and help understand what attitudes or what things would be better. And then we can take some of that data and process it and use it to do that race engineering component. So again, back on the geometry is the first thing we have to focus on. How do we get that? And if we had CAD, if you're in control of CAD, and it's becoming more common, programs like SolidWorks are out there where people are doing their own CAD. We've worked with companies like some hot rod shops and land speed guys that are doing their own CAD. So it's not like CAD is reserved for high-end engineering and large companies. There's a lot of people doing it, and it really, once you kind of get over that hump, it makes it a lot easier to get into doing things like CFD. But if you don't, 3D scanning is also becoming more prevalent. We've done many projects. We've got 3 examples here of a land speed car, a cafe racer, and a road racing Porsche that all were, there's no CAD that exists for these things. They're either completely unique vehicles. Mostly in these 3 cases, they were completely unique vehicles that were handcrafted. So we go and with a laser scanner, handheld scanner, basically reverse engineer that car, capture that 3D data that can then be used for both CFD and other things. Then you can use that to modify the body. You could use it to make molds. You could do it to make anything. So quite useful just beyond what we're talking about here. So then the next step is this geometry input into the CFD workflow. And for this, I'm gonna cheat a little bit, and I've got a bit of a demo video. And this work for us is probably, if you have everything organized, it's a half hour or an hour's work to input everything and double check it. But I've made it look like it's 3 minutes by speeding this up, just so I can talk over it, because I know we're going to limit an amount of time today. But as you can see, we have a web interface. We can upload all the parts of the car, the body, the wheels, everything that we need to put that car together. Then we upload those to our to the supercomputer. We can see a status of how these things are uploading. And then once we've uploaded them, we have to do a few things. We have to take from the CAD or the known data that we've got from scanning and tell the computer where things are located. The radiators, for instance, we have to describe the characteristics of the radiators. We have to describe where the wheels are and where the rotation center is. All the typical engineering things that you would have to do, like even in a lap sim, like Danny was showing yesterday, that you have to have all those points and understand them and input that. So that's what we're doing here. We're checking everything, understanding like where the front wing is, where the pivot points on the wings are, so we can make adjustments later down the road. And then we're loading all that geometry in to describe this assembly of parts that we want to take to the wind tunnel and test. And once we're done with all that, kind of move forward, and we can pick an assembly, essentially build an assembly of all those parts, and call that our new baseline. And then we can create a run. And from this, we want to set a speed, a yaw angle, all these things that we're talking about that describe the attitude of the vehicle, what ground clearances we have. And for race cars, typically with a formula car, even sports cars, this ground clearance and where we're holding the attitude of the car is critically important to the aerodynamics. So that's why typically when we talk about mapping, we're talking about what it's like in relation to the ground or the air. And especially with a formula car like we have demoed here, that ground clearance is critical and changes the aerodynamic performance hugely. So we have to be very conscious of it. And we're talking down to the millimeter type accuracy here. So once we've got that loaded up, we can obviously we have a viewer here. We can see the geometry, make sure it all makes sense, that we've got all the parts we need to put it together. Understand where all the, we've got radiator cores, we've got the suspension and everything loaded up correctly. And then we can make some, once we've got that baseline run, we can then duplicate the run and just simply change certain things like the ride height, the ground clearance, the wing angles, the speed that we're running at. Any of those things, any of these variables can then be edited. I create a new run, save that, and then move on to another run, duplicate it, continue to create this map of runs that we want. And once we're done with all that, then we've saved the last run, and then we can actually submit that run to the computer. So the next thing that happens in the process is the actual solving of the case. And just to remind everyone what's going on, what we're talking about here is CFD. So it's essentially a virtual wind tunnel. So we've taken that 3D model and then we've told it all the things that we need to do as far as the wheel spinning, the road moving, the air blowing, what's going on there. And then from that, we have to solve it. So part of that solve process is we create we virtualize the air by breaking it into tiny little blocks. And at the top here, you can kind of see a slice through the mesh. So we build this mesh of tiny little cubes that are all in the air, and then we're solving math in each one of those cubes. And for instance, with this F3 car, it's probably about 80 million little cubes that we're solving math in as the air flows through. So the air comes in at a speed and a pressure, and then something happens to it, the body deflects it, and then we calculate the vector, and that goes on and on and on. And that's what the computational part of computational fluid dynamics is. So that's what we call the solve. So then once we've solved that, then we have all that information captured for all those 80 million cells. Now we can post-process it. So we can look at what is the velocity, what is the pressure, what is the resultant forces on the car itself. And that's what we call post-processing. So post-processing. So when we post-process, we are collecting that data, we're summing those forces, and we're also making images and movies, streamlines, pictures of the surface pressures. We have all that information, so we need to render that. And that's a fairly time-consuming process. And what we've done is kind of automate that so that every single time you get the same numbers out, well, not the same numbers, but the same, you're filling in the same columns, the same parameters. We're pulling that data out for each run, and we're getting the same images for each one, so we can then do comparisons. So that's really what's happening in that kind of black boxed CFD thing that we're calling the virtual wind tunnel. We're going to send it off, do that run, and then we're going to get the data back. But there's a lot going on there for the 12 hours while we're doing it. So the next thing we want to do, the fun part, is then get into the data. So I will flip back over. Let's see. Let's flip back over to the actual. So then when we've run those runs, we'll come back in the results interface. We'll gather all the data, it'll come in, and we've got a table of data that we can look at. This gives us all our forces, all of our moments, everything that we need to understand what's happened with the vehicle from a force standpoint. But at the same time, we can also kind of look at the run itself, like to the individual run. What were the forces we got? Are we monitoring things like the flow through the radiator? We can also break down the forces because we have all the information. We can say, what was the drag on the body? What was the drag on the floor? What was the drag on the wheels? And then as we make changes, we can understand where we're affecting that. We can also look at things like what actually happened during the CFD run. Did things, what we call as convergence, did they kind of find a nice level and everything looks like it's solved correctly? So there's a lot of things. Then we get images back out after we're done. So we can look at all kinds of things like surface pressure plots. We can look at different ways of understanding how the drag is generated on the vehicle. And as I said, we've automated this to the point where we get the same runs or the same images and same data every single run we do. So then that allows us to go in and do something like compare runs. So if we have a run here that we've got a front view of the car here, we can actually go up and look at different changes, and you might be able to see it's fairly subtle in this one, but we're actually flicking between different runs, and we're looking at quick comparisons of what's happened to the pressure on the car. So this allows us to be an analyst and look at the aerodynamics and understand what may be happening on the vehicle itself. So another thing that we can end up doing is doing some plots. So if we wanted to create some plots and try and understand what's happening with, let's say, lift and drag in this case, we can do a comparison. We know we've done a ride height sweep here, and we can see that at a certain ride height, or we've got a Pareto front here of possibly getting more downforce for a given drag. So just starting to analyze the data, starting to look at things like that. So going back to further post-processing, we do have the kind of result side of things as well, not just for car stuff, but we've also got a method that if we're not using the application itself to create the CFD, we can actually ingest data from other places. So another CFD solver or wind tunnel data, and we can use all that data in one area and start comparing those things. Then once we've got this data, again, what do we do with it? When we, if we kind of go back and remember some of these plots from earlier, where we want to create these maps of the car and then actually go use that. An example that I can bring up quickly is we can build a spreadsheet. So we can take all that data that we had that shows those plots. We can create some curve fits. We've got these data tables. So for every ride height, we've created a lift, drag, balance. We can take that and input it into lap simulation like Danny was talking about yesterday. It can be used on a driver in the loop simulator, or it can just be used like in this case, this is an old setup tool that I had where we're comparing one setup to another. And we want to come in between sessions, change the ride height, and we want to know how much front wing we have to change to rebalance the car, keep the balance the same in the middle of the corner. Even though we've changed the pitch attitude of the car, we can adjust the wings to make sure that we have exactly the same aerodynamic balance in the middle of the car. We can use, once we've mapped out this whole parameter space, we can create tools like this that allow the race engineer to then go in and try different things, experiment, or make a change with confidence and say, oh yeah, it looks like we've got the data off the car. And this is what happens at the top end of motorsports all the time. You're watching the telemetry, you're seeing that the aero balance is a little bit off. Okay, we need a half a turn of front wing. How do they know that? That's because they map this out and they understand that to do X% of aero balance, it's this much front wing to do that. They're not guessing. This stuff happens because we've got this data. So then one other great thing that you can do, if you've gone and run all these tests, whether it's in wind tunnel or CFD, you can go back and kind of like build a model and then develop like a scatter plot, basically, of saying, this is every permutation and combination of ride height or part that we have on the car. And then what ones are actually useful to us? Well, in this case, since we've got downforce on the vertical axis and drag on the horizontal axis, we would want, as an engineer, to say, I want, for a given drag, I want the most downforce, or for a given downforce, I want the least amount of drag. So you can find what we would call, in engineering or math terms, a Pareto front here. So it's that edge that you want to be on all the time. I don't want, if I need 2,000 pounds of downforce, I don't want to be over here with 860 pounds of drag if I can be 840 pounds of drag for the same downforce. I'm going to go, several miles an hour quicker for that, right? This being a speedway car or something like that. So this is what, in the end, the purpose of doing all this is to gather all that data, understand all these permutations and combinations, and then do some studies both offline and at the track and understand where those points are. So that's really where I wanted to get today, Brad, to kind of add a little bit more detail into what we ended up doing here to try and streamline that. Be able to have more people, go into this, be able to gather data that they need, and not just the top level guys. So
this is incredible. A quick question: looking
Sure.
at the TSA or the TSAuto, say on the TotalSim
Yeah.
website, it says using TotalSim's TSAuto app is an intuitive experience and requires little to no training with a user-friendly interface. Who can use this? I mean, do I have to have an
as a marketing people that put that out there? No, it's true. I think we've designed it for people that have that knowledge, have some ability to control their 3D data and understand it, and then want to manipulate that. So we've done it a couple ways. If someone has all the CAD they need, we have several customers, even some guys that do streamliners for Bonneville or whatever, that they've drawn their whole car. They can upload it and they can do some studies. They're controlling the shape. They want to study it, right? We have other people that don't have the ability to do that. So we've gone and scanned the car, built the model. We can set up the baseline, and then maybe they can iterate, right? Then it's there for somebody to say, oh, I'd like to study this or study that. So that's kind of where it's set at, and there's some training involved in that, but it's less training than starting CFD from scratch, at a command line or whatever. So tried to strike a balance between ease of use and the there's still some difficulty in there, but it's reduced to a certain point, that's for sure.
Yeah, well, I mean, it simply looks like here's a great entry into, we've already done a lot of the work for you. Now it just becomes your specific thing. It's not like people have to,
Right.
figure out something from scratch. It's incredible. And even just watching your presentation, but also having gone through the website, how useful a tool this can be for a lot of different industries, but more importantly, what we're talking about here, the racing industry. It's incredible.
Yeah, and I don't want to downplay the geometry creation side of it. It's still a barrier to entry, but what we've seen, from when we started this company 12 years ago and what we were doing 20 years ago, when I was at Ray Hall or Nathan was at Williams, that CAD creation is so much easier these days, but it is still a thing that you have to invest in, and it's an upfront cost to get in there. But once you're in there, then, these things are going quicker. And as we've seen with a lot of technologies, this stuff is just getting easier and easier by the year. And I'm seeing more and more people, and I don't want to, say it's like, but it's like it's going down market, right? This is not just reserved for the top level anymore. It's moved down to the serious amateur or the next level professional. So that's what we're seeing happening. And I think that's happening with a lot of technologies across the sport, whether it's driver in the loop sims or other things.
Yeah, I think the most important thing is you're showing us this is accessible to people. It takes something, but it's accessible, which is great.
Right. Yeah, and we're here to hold hands and help people do it. Show them the way.
Thank you, Ray. Thank you so much. What a great presentation. Always a pleasure to see you. We'll see you.
Likewise, Francis.
As well too. And thank you, for being with us. What a great week. And, you follow some pretty heavy hitters, and
you put me in a good time slot.
I think so. I
appreciate it. I appreciate it. I don't know if I can live up to Zach or not, but try and do my best.
The concept for EPARTRADE is basically, in my opinion, there's a big hole in the internet. So the internet started many years ago, but there's never been an online business community for racers on the World Wide Web. The need for EPARTRADE is actually quite obvious. Basically, people in the business of auto racing need a place online to hang out and get their problems solved.
It's extremely simple for a buyer or for a supplier to interact on the platform. The first thing you need to do is sign in, which is free. And the second thing is, when you see a product that you're interested in, all you need to do is click on request more information. If it's a company, you click on request more information, and then from there, it is forwarded directly to the buyer or to the supplier.
You can go to epartrade.com, you become part of a community of businesses in racing, and it makes sourcing products much easier than just on the internet or using Google.
At EPARTRADE, there is no e-commerce. It's literally a connection just like at a trade show. So now, any time of the year, a buyer could reach out to a supplier through an email.
More than that, it's a place to go just to keep current every day. So it's a good place to start your workday in your racing business or in your offices of your professional race team. And you're current when it comes to new technology, industry news, technical papers, technical videos, all of that and more. We're not looking for a million hits per day. All we want is people who are really the volume buyers of racing products in the racing industry to be part of the little world of EPARTRADE. We have racing businesses participating from around the world. So you get suppliers from around the world, you get buyers from around the world.
EPARTRADE really eliminates having to travel, closing down your shop. Now you have a place to showcase globally your racing product and technology.
There are two types of people, racers and everyone else. Racer Magazine is for those who believe that racing is a way of life. Racer embodies the excellence that defines a sport driven by passion, courage, and ingenuity. Get 1 year of both Racer's print and digital edition for only $39 with instant access to our entire digital issue archive. Subscribe now at info.racer.com.